Let's prove divisibility and inequalities under the principle of mathematical induction. For this last set of expressions that we need to prove using the mathematical induction, we need to understand the concept of how divisibility works and how inequality works. Let's talk about divisibility first. When I talk about divisibility, a number is divisible by a specific number if that first number I'm talking about has a factor of the second number. Let me put it this way. 10 is divisible by both 5 and 2 because 10 can have a factor of 5 and 2. 100 is divisible by 10, divisible by 4, divisible by 2, by 25, by 20, because 100 can have those factors. So if we talk about proving number 1 and number 2, because they are on divisibility, we need to understand that we need to create an expression wherein we could express a factor of that expression to be divisible by the given concept. Let's talk about number 1. Here, we need to show that n squared, sorry, that's n squared. We need to show that n squared plus n for all numbers which are an element of positive integral set, a set of positive integers rather, is divisible by 2. Still, we're going to follow the same steps here. And what are those steps? Step 1, we need to show that the divisibility is true, or it holds rather, when n is equal to 1. Second, we need to show a statement where n is equal to k. And for the third step, or if you don't like a third step, still continued step for step 2, we need to show or assume an expression when n is equal to k plus 1 and show that it's still true given the situation. So here, for step 1, we need to show that if n is equal to 1, it's still divisible by 2. And how do we do that? Let's try to substitute here the value of n, which is 1, to the given expression. And you will have here 1 squared plus 1, which is 1 plus 1 and 2. We already know that 2 is divisible by 2, but we could also express 2 as a product of 2 times 1 just to emphasize the next steps that we're going to do later. This means that 2 is really divisible by 2 because it has a factor of 2. Well, in fact, 2 is 2 times 1. Okay? That means the first statement is now satisfied. The second step is where we are going to assume that n is k. So instead of this expression, you will have the expression k squared plus k. And this should be divisible by 2. How do we create a situation or an expression wherein we could show that k squared plus k is divisible by 2? Not by words, just for symbols. To do that, we could say that k squared plus k is equal to any number that has a factor of 2. So let's just simply use 2x. What is the purpose of that 2x? Similar to what actually extended here in number 1, or step 1 rather, that we could express 2 as a product of 2 times 1. This is just to emphasize that any number that's divisible by 2 should have a factor of 2. So in case that this is now our symbols, where we change n as k, so we have k squared plus k, we can make an expression here or equate it to an expression that has a factor of 2 to tell us or to show that this is really divisible by 2. So we have 2x here. Since we could apply any value of x here, let's just say 100. 2 times 100 is 200, still divisible by 2. Let's just say 13. 2 times 13 is 26 and still divisible by 2. So this x here is just any value that you could think of that could still represent this as as an even or a divisible by 2 expression? Well, if you don't like x, you could use other variables. Just don't use k or n because it has already been used. You can use 2a if you want to, 2h if you want to, 2m if you want to. But since we are just going to have our simpler example, let's have it as 2x. Again, this is the purpose of 2x here. It's not like it what happened, why is it that there is 2x or there is x now. That is just a representation that this expression 2k k squared rather plus k is divisible by 2. So with this, we need to show an expression that we are going to manipulate later on as proof that this it's still divisible by 2. That is actually when we try to substitute as n is equal to k plus 1. So we are going to show that this value here, k squared, k plus 1, or the square of k plus 1, as we substitute k plus 1 to k, plus another expression k plus 1 must be divisible by 2. Now here, so that we have different expression, you may use here 2y. This is what we are going to show later. Unlike the first two videos, which are focused on identities, and we are manipulating the expressions rather in such a way that we could come up with the endpoint. Here, no need for talking about endpoint. We just need to show that this expression is really divisible by 2. So let's try to manipulate this, right? This expression only, because this is what we're going to show later on, right? So we have here this expression k plus, or the square of k plus 1 rather, plus k plus 1. Okay, so we have this now, k squared plus 2k plus 1, the square of a binomial, don't forget about that, equals here, plus k plus 1. And then you will have here k squared plus 2k plus k is a 3k plus 2, which is 1 plus 1. Now, how do we show this expression as still divisible by 2, or any expression with factors of 2, where in fact we don't have value for k and or nor k squared? We do have a value here earlier that we could have assumed here, this expression. So we could actually manipulate this in such a way that we will have here k squared is equal to, subtract both sides by k, so you have 2x minus k. This is the algebraic representation of k squared. And why do we need this? We can simply substitute it here so that later on we could only have k but no more k squared. So to continue, k squared is actually 2x minus k, this value here, and still plus 3k, and you have here plus 2. Further, you will have 2x, that's negative k plus 3k is positive 2k, and plus 2. Take note that our goal is to make sure that this expression here is divisible by 2. By saying that, we need to make sure that the final expression here has a factor of 2. I'm talking about here 2, 2, and 2. And when we factor that out, you could have here x plus k. Factor that, you have here 1. With this expression now, we could see that whatever the values of x and k here, as long as they are integers, since that's what we're talking here, they are always going to result to a value that is divisible by 2. So let's say x is 5 and k is 3. So 5 plus 3 plus 1 is 9 times 2, 18, still divisible by 2. Or if you would like to, we could always assume, because this is our goal earlier, we could always assume that x plus k plus 1 could be any variable y. So with that, we can substitute here. So this is actually 2 y, and we have reached here our goal. This is how we show the proof for the expressions under divisibility. Again, we have started with n is equal to 1, and if it's satisfied, you need to continue for the next step. N is equal to k. Simply change the variables here to k and assume an expression here that could correspond to divisibility or a divisible by 2. That's why you have 2x here. And take note, that's very important. As we proceed later on for step 3, we could actually manipulate this so that we could simplify the step 3 easily. Before we proceed to step 3, we need to determine what needs to be proven, and that is when we change the k to k plus 1. And again, here we just simply change to y to represent another value or yes, expression or value of the expression is that's still divisible by 2. And then manipulate this left hand side, and then we use this expression here to come up with the final result. This is the proof that this is true. Number 2 is still divisibility, but now it's divisibility of 3. So instead of 2x now, we can use a 3x. But first, let us start with step 1. Step 1 is when n is equal to 1. And let's show if this is true. So you have 1 cube minus 1 plus 3. 1 cube is 1 minus 1 plus 3. That's 0 plus 3, which is also 3. And 3 is divisible by 3. Therefore, the step 1 is already satisfied. Or you could also again write this as either 3 times 1 just to show the expression just like this, that any number that has a factor of 3 is divisible by 3. Step 2 is when we assign n as k. So instead of this expression, you will have k cubed, sorry, that's k cubed minus k plus 3. Similar to the step 1, we need to make an expression here to describe that this expression is really divisible by 3. And to do that, we could have here equal to 3x. X could again any other value because we have shown that the number or any number that is divisible by 3 should have a factor of 3 for it to be true. This expression now stands for that. To show that this is really true for all positive integers, we need to come up with an expression where n is k plus 1, the expression that we are going to manipulate later. By the way, let me move this a little bit farther so that we could talk about it later, so that I also have another space here. So looking back to step 2, this could actually become k, or the cube of, sorry, the cube of k plus 1 minus, you have here k plus 1 plus 3 should be divisible by 3 as well. Or assign us with 3, y, and y could any other value. Again, the purpose for this is just to show that it's divisible by 3, for it has a factor of 3. This is now what we are going to manipulate here, this step here. And to do that, let us have step 3. Let's manipulate that. You will have the cube of k plus 1 minus k plus 1 plus 3. You already have a special product for this, but you could also use the binomial theorem for its expansion or the Pascal's triangle. This actually equal to k cubed plus 3k squared plus 3k plus 1. This is just the whole expression of the cube of k plus 1. Minus, you have the next expression, k. Take note of the grouping symbol. Distribute that minus 1 here. And you have here plus 3. Again, what happens here is this. When you remove this grouping symbol, do not forget that the sign here will be changed. Instead of plus 1, we have minus 1. But plus 3 is still plus 3 since it doesn't have, it's not part of the grouping symbol here. To simplify, you will have here k cubed plus 3k squared. And then you have plus 3 minus k is you will have plus 2k. 1 minus 1 is 0, so you will have here plus 3. However, for this form here, we cannot see a factor of 3 for all the terms in such a way that we could just simply copy the step here. Here, we don't have factor of 3 for the first term and the third term. So we cannot do that. However, we could apply the same step that we did here in solving the k squared earlier, and whatever the result, we substituted it in the equation to continue down and see later on if we could come up with a result. So here, we are going to use this expression for our value to be substituted here. So let me bring it down. So this expression now is k cubed minus k plus 3 is equal to 3x. We are going to manipulate this in such a way that we are going to solve for k cubed, and whatever the result will be, that's the expression that we are going to substitute it here, and see later on as we move further down if we could come up with an expression that looks like an expression that is a factor of 3. So we have here k cubed. Remove these two terms, you will have 3x. The minus k will become plus k, and the plus 3 will become minus 3. This is not the expression that we could substitute for k cubed here as we continue. Hence, k cubed now is 3x plus k minus 3 plus the additional terms 3k squared plus 2k plus 3. So we have this expression here. Let's have 3x. And let me arrange the terms with k into decreasing order of exponents. So you have plus 3k squared. K plus 2k is plus 3. 3k. Negative 3 plus 3 is 0. So this is now our expression. As we see now, we have factors of 3 for each term. So we could factor it out. 3 times the expression x plus k squared plus k. This is now an expression with factor of 3, and that's very clear to state that this is now divisible by 3. Or, again, you could assume that y, so that we could reach here, is equal to x plus k squared plus k, so that we'll have this expression here, 3y, and we have actually reached our goal. This is how we prove divisibility using the principle of mathematical induction. But wait, we still have one more item here. The last item is for inequality. To prove inequality, we need to understand that we should not stick with the two expressions only. Now here's the thing. If we have 3 is greater than 2, it's also true that if we're going to add another numbers than 3 and 2, we could create an inequality. Let's say, again, 3 is greater than 2. But if 5 is greater than 3, then 5 is also greater than 2. Again, 3 is greater than 2. But if we have a number which is 5 that is greater than 3, then 5 is also greater than 2. That's actually the transitive property of inequality. That is why, if we talk about proving inequalities using mathematical induction, we could actually use a value that is bigger than the bigger value or smaller than the smaller value. Let's talk about number 3. Here, we are going to show that 2 to the power of n is greater than 2n for all n, which is element of the positive integers, but strictly it starts with 3. So 3, 4, 5, so on and so forth. Our step 1 here is still step 1. However, we are not anymore going to use n is equal to 1. Why? Because we have here the restriction that it starts with 3. And after all, if we're going to substitute 1 here, 2 to the power of 1 is 2. 2 times 1 is 2. It does not satisfy the inequality. Take note, it has a restriction. So instead of 1, we could apply here n starts with the smallest possible value for n, 3. Okay, so let's have here 2 cube. Is it greater than 2 times 3? You have here 2 cube, which is 8, and you have the other side is 6. The answer is yes. Therefore, it satisfies the given inequality. The next step is still the application of changing the value of n to k. Okay? So we have here this expression 2 to the power of k must be greater than 2k. And this is what we are going to show later on. And this is actually the expression that will be used to get the item that we are going to show. That is actually if n is actually k plus 1. So out from this, what we are going to show is 2k to the power of 1 must be greater than 2 times the quantity k plus 1. Sorry, 2 times the quantity k plus 1. So this is what we're going to show later. To do this, we have many ways to show this one. The first alternative step for step 3, in such a way that we could show this expression here, is if from this expression, we could actually multiply both sides by 2. And take note, if we're just going to multiply both sides by 2, it will not change the inequality. That would mean we are going to multiply 2 to the expression 2 to the power of k, and it's still greater than multiplying 2 to the expression 2k. We are multiplying positive numbers on both sides. Rules or inequality, it will not change. And let's see if it's really an expression that could actually be the same as this. Okay, but this is what we're going to show, the blue color. So we have here this expression, and the loss of exponent tells us that if we have the same base, we add the exponent. The exponent for this is 1. So you have 1 plus k, and it's greater than, you'll have here 2 times 2k, which is 4k. This expression here is actually 2 to the power of k plus 1. We have reached this side here. However, the other side, it's not this expression. It's just simply 4k. This is what I have told you earlier about not necessarily sticking to the given two given expressions. You can think of a bigger number, a smaller number, or a number in between, or an expression rather in between to satisfy the situation. 4k can be written as 2k plus 2k. Okay, 4k can be written as 2k plus 2k, and this is still 2k to the power of k plus 1. Now, if we have here 2k plus 2k, definitely this expression is greater than 2k plus 2, because this expression now doesn't have any variable. Look at what will happen here. Simply cover this first. Let us not write this first yet. Look at this. If we have a k here, which is all values greater than 3, because it starts with a n is equal to k, so it's similar value to that. If you have here 3, 2 times 3 is 6. Here is 6 as well. 6 plus 6, this will become 12. Here, 2 times 3 is 6 plus 2, you have 8. Then definitely 12 is greater than 8. If you're going to choose other values other than 3, all values greater than 3 as long as they are integers, this is actually true. Now, going back to the situation where I listed this earlier, we have here this expression, okay? And with this situation, we could use the transitive property, and by removing the middleman. When we remove that, what expression we have now is 2 to the power of k plus 1, now greater than the expression 2k plus 2, which could actually be factored with 2. So you have 2 to the power of k plus 1 is greater than 2 times the quantity k plus 1. As you can see, it's now the same as our goal. Again, the thing here is we added a number, that is not part of the concern, but in the middle of those two concerns to satisfy the situation. The other alternative here is when we, instead of multiplying both sides by 2, we can add both sides by 2. So you have here 2 to the, let me use another color. We have 2 to the power of k plus 2 is still greater than 2k plus 2. Out from this expression here, we just simply added 2 on both sides, plus 2 here and plus 2 here on this side. Purpose for this is that we could actually use here the factoring on this side, and you will have this expression 2 to the power of k plus 2 is greater than 2 times the quantity k plus 1. So we can show already the this side here. Earlier we started with the left hand side for this alternative. For the second alternative, our goal is to first see to it that the right hand side matches this. Here, the same thing is concerned. We could actually add another number, okay, to greater than this in a form of this expression. You will have 2 to the power of k plus 2 to the power of k, and this is greater than 2 to the power of k plus 2. This expression here, a value which is more greater than this, or rather, greater than this. Take note of this value of k is greater than is 3 or bigger. So if you have 2 cubed is 8, 2 cubed also here is 8. 8 plus 8, 16 for this side. But if this side here will have 3, 2 to the cube is 8, plus 2 is 10. So 16 is greater than 10, and that is actually true. Our point here is we added this in the inequality, and by continuing writing this expression here, it will look like this. Just like what happened here that we have added something here earlier. Now, let's cut the middleman, and we could have this expression, orange. You have 2 to the power of k plus 2 to the power of k is greater than 2 to the times the quantity k plus 1. You have two expressions that are the same, so you can factor that out. 2 to the power of k, so you have 1 plus 1 greater than 2 times k plus 1. Then you have here 2 to the power of k times 2 is greater than 2 times the quantity k plus 1. Loss of exponents allows us to add exponents. So you have here 2 to the power of k plus 1 is greater than 2 times the quantity k plus 1. Same thing, we have reached this concern. For improving inequality, again, as I mentioned earlier, it's all right to consider other expressions that could be in the middle of those two or bigger or larger, just to emphasize your point. So these are the two alternatives in proving in inequalities under mathematical induction. This is how we prove this, and this is actually true. You may use this as part of your review, including the notes earlier for the divisibility for, as part of your preparation. See ya.